Hey guys, my name is Didi Jimenez, and today we're going to go over the function of pulmonary surfactant. Okay, so to start off, we're going to go over the composition, location, and the function of surfactant. As a complex mixture of lipids and proteins, pulmonary surfactant is secreted by type 2 alveolar cells. This complex and highly surface-active material is in the fluid that lines the alveolar surface of the lungs. It is important to note that surfactant is extremely helpful when it comes to lowering alveolar surface tension. The extent of hydrogen bonding between molecules and at the alveolar air-water interface is decreased by pulmonary surfactant since there is a very low cohesive force between surfactant and a water molecule. Surfactant provides two benefits due to its ability to lower alveolar surface tension. The first benefit is it increases pulmonary compliance, meaning that the lungs don't have to work as hard to inflate. Number 2. Surfactant reduces the tendency of lung recoiling, withholding them from collapsing so readily. These two benefits are extremely important in maintaining lung stability. Now, moving on from those three things, we're going to go over its mechanism. The lung is divided into myriad tiny air sacs, which cause an advantage of increased surface area. This tremendous amount of space is where the exchange of oxygen and carbon happens. But that causes a problem in the amount of space maintaining stability of all these alveoli. Remember that the alveolar surface tension generates a pressure that is directed inward, squeezing in on the air in the alveoli. Picture a spherical bubble, as seen in the representation here, the top, right here in this area. Picture this circle. Now, taking in the law of Laplace into consideration, the inward direction collapsing pressure has a magnitude that is directly proportional to the surface tension and inversely proportional to the radius of the bubble. With this equation, 2T over R equals P, where P is the inward direction collapsing pressure, T is the surface tension, and R is the radius of the bubble. So again, the equation was P is equal to 2T over R. Due to the inverse proportional collapsing pressure on the radius, the smaller the alveolus, the smaller the radius will be, resulting in a bigger tendency to collapse at a given surface tension. On the other hand, if there are two non-proportional alveoli with the same surface tension connected by the same terminal airway, there will be a smaller alveolus. This is because there is a larger collapsing pressure generated, which tends to collapse and empty its air into the large alveolus, as seen in our figure at the top. That is this smaller one releasing into the bigger one because of the surface space. In normal conditions, collapsing and blowing up of bigger alveoli normally doesn't occur with small alveoli, leading to our topic of pulmonary surfactant, which causes a decrease of surface tension. The decrease being bigger in small alveoli in comparison to large alveoli because of the molecules being crowded in smaller alveoli. With larger alveoli, there is a bigger spread of surfactant molecules, causing it to have less of an effect. In smaller alveoli, with a surfactant-induced lower surface tension, causes an offset in the effect of their smaller radius in determining the inward direct pressure, meaning that surfactant causes a collapsing pressure to be comparable between both small and large alveoli, and it also reduces the small alveoli's tendency to collapse and dump its contents into the larger alveoli. All in all, this means that surfactant aids in stabilizing the size of alveoli, keeping them open, and making them available for gas exchange. Now, digging into why this is important. In this case study, we're going over persistent respiratory distress. Respiratory distress normally occurs in infants. When they're younger, their lungs don't stay open, so surfactant aids in that so they can breathe. I had a premature baby, so I know that part. But in this study, presented a female baby who was only 17 days old was brought in because of persistent respiratory distress. And the malformation of lungs called CLE, or congenital lobar emphysema, is one of the main causes of persistent distress. In our picture to the left, we have an x-ray that showed overinflation of the upper left lobe, and on the right side, herniation of the chest with mediastinum shift to the right, increasing the chance of it being a left upper lobar emphysema. Pneumothorax was ruled out because of the lack of pleural line visualization. A CT scan confirmed the diagnosis, showing an hyperinflated left upper lobe with vascular attenuation, which correlated with the shifting of the mediastinum with herniation of the left upper lobe. Operation occurred, baby was discharged, and had a wonderful follow-up appointment. In conclusion, while lung malformation is rare, CLE is another cause of respiratory distress because of the trapping of air in the lungs due to the malformation. So now for our final slide. These are our resources, and with the presentation we know that the respiratory system is highly important for us to live, and there's the resources in case y'all want to go over more. Thank you guys. See you next time.